Okay, so it's a pleasure to have Shirley Lee with here us today. She's going to talk about theoretical challenges in modern neutrino experiments. Shirley is a postdoc at SLAC, soon moving to Fermilab. So please take it away, Shirley.
Thank you. Thank you for the invitation. Okay, and please stop me anytime during the talk if you want to ask questions. And I'm not sure I can see you, so please just unmute and speak up. Thanks. Okay, so we now have a suite of large-scale neutrino oscillation experiments, both ongoing and in planning stage. And I want to talk about, I think as a theorist, there are quite a few challenges we face to make sure that these experiments have successful outcomes. And so today I'll focus on what I think is the most critical theoretical challenge, and that is to understand GeV neutrino nucleus interaction cross-sections. And so the background picture accurately reflects how I feel about the current situation, that it's a giant pile of mess. So I'm as excited about the opportunity as the cat about the yarn. Hopefully towards the end of the talk, you can understand why. Okay, so after 20 years of aggressive experimental program, we've established the three-flavor neutrino oscillation paradigm. And hopefully this is a very familiar slide. So we know that there are three neutrino flavor eigenstate, nu e, nu mu, nu tau, and there's three mass eigenstate, nu1, nu2, and nu3. And these two bases are rotated with by mixing matrix, which is controlled by three mixing angles, theta 1, 2, theta 1, 3, theta 2, 3, and one delta CP phase. And in addition to compute oscillation probabilities, we also need to know the square mass differences. So of all the parameters, I would say for most of them, we've entered, so all the thetas and delta m square, we've entered precision stage that, the measurements nowadays are like a few %. And with the next generation, they'll be super precise. And the last two unknowns are delta CP and mass hierarchy. And they are the, say, bread butter measurement of next generation oscillation experiments. Did I hear a question? Okay, I'll take that as no. Okay, so there's a variety of different oscillation experiments, and I think it's fair to say that the type that start to take center stage is the type of the so-called long baseline oscillation experiments. So the setup, they are pretty general, so I'll use Dune as an example throughout my talk, but they're basically all similar. So you have an accelerated beam that produce muon neutrino of, say, a few GeV. And then you let this muon neutrino propagate very long distance, Dune being the longest one, 1,300 kilometer baseline. Then at down the stream, you measure how much of the nu mu have turned into nu e in your far detector. And measuring this probability in both neutrino channel and anti-neutrino mode, which means that the beam produced nu mu bar, and you measure how much of that nu mu bar have turned into nu e bar. So neutrino and anti-neutrino mode gave you both delta CP and mass hierarchy. And in terms of cross-section physics that I'll talk about, pretty much everything I said about Dune applies to Nova, which is basically the current generation version of Dune. And the physics is a little bit different for Hyper-K, that's the future generation, or T2K, that's the current generation. But if I will not talk about how it's different for Hyper-K and T2K, but if you're interested, ask me later. Okay, so that's the general experiment setup. So for cross-section today, I will cover three aspects. So first is just conceptually, how do cross-section actually affects experimental measurements? And then I'll discuss roughly what are the current theoretical uncertainties. And lastly, and to end on a positive note, how to improve cross-section. And a disclaimer is that these three parts are not perfectly connected. And there seemed to be a little bit logical jump. And that's because I picked the three aspects that I've worked on, and that's easy to explain. So if any part seems to be missing, please just ask me. Okay, so I'll start with just conceptually, how do cross-section impact oscillation measurements? Okay, so how do we measure oscillation measurements? How do we carry out oscillation measurements? So the thing you want to measure is the left panel. you want to measure oscillation probability that looks some sort of wiggle as a function of true neutrino energy. And again, basically, we want to measure this for neutrino and antineutrino. So oscillation probability is basically in practice, that means two things. So first, you take what is the event rate after oscillation. So that's the thing you measure in the FAR detector. And you want to divide it up by the event rate that is before oscillation. So both as a function of true neutrino energy. And so the FAR detector is a measurement, but the thing on the denominator should be a prediction. Basically, event rate before oscillation, meaning that you have to predict your flux and you have to predict your neutrino interaction cross-section as a function of neutrino energy. And you multiply that should give you the thing on the bottom. Okay, so at this level, you might think, I already identified how cross-section matters. It's in the prediction for the bottom panel because, naively, if I get the cross-section as a function of neutrino energy wrong by, say, 5%, that directly translates to an error of the oscillation probability of about 5%. Well, and let's say that's the case for now, and just see what level of precision we should aim at for cross-section prediction. So here I plot the actual oscillation probability for DUNE in neutrino channel as a function of neutrino energy. And I pick 3 values for delta. Assuming the true value of delta is 0, the oscillation probability would be the solid line. And for DUNE CDR, the nominal accuracy at 1 sigma on delta is about 10 degrees. So if delta is plus or minus 10 degrees, the oscillation probability would be the dashed lines instead. And most of the oscillation power, and you just have to take my word for it, is in the last bump. So despite there are 3 structures, I would say, imagine most of the measurement happens between 2 GeV to 10 GeV. So then you see that these oscillation probabilities actually are quite similar. The peak only differ by 5%. So this sets a scale of roughly we're doing a 5% measurement. We want all our calculations to be about 5%. Okay, but that's not what actually happens here because we don't actually rely on theory calculation to predict the bottom panel because of very large uncertainty. Instead, what we do is we build another detector very next to the beam, and that's called the near detector, and measure this thing directly. Okay, so now you might think, okay, since we don't predict, we measure this whole thing, then both top and bottom panel are measurement. We don't need cross-section prediction at all. Well, that's not the case because near detector does not work perfectly. And there are many reasons for that. I'll pick the 2 that's easiest to explain. So the first is the flux in your near detector and the flux that would arrive at the FAR detector if there were no oscillation are different. So the left panel explains the situation. So the beam is this gray, coming from this gray cylinder. And your near detector, because it's very close to the beam, are seeing a very small solid angle portion of the flux. Oh, sorry, that's wrong. Because near detector is very close, it's seeing a very large portion of the solid angle. And because your FAR detector is so far away, it's only seeing like the most forward region of the beam. And neutrino beam are not isotropic. So whether the flux is in the very center or on the sides, the energy spectrum is different. So on the right panel, I showed this quantitatively. So even without oscillation, the flux seen by near and far detector, just because the solid angle difference is the blue versus green orange line, and you see that the difference is larger than the 5% scale that we're trying to aim for. So near detector doesn't actually measure the flux perfectly that you need to do the division.
Sorry, Shirley, I just had a question there.
Yes.
That's for DUNE, the plot that you have on the right?
Correct.
And if I vary the energy, so for example, the proton energy, like they have these different energy tunes for the beam. Yeah. If I go to higher energy beams, for example, does this get better or worse?
Oh, excellent question. I do not know the answer. You mean the difference? I'm not sure. Yeah. I don't know the answer actually. I think they have two setup, right? as far as I know.
Yeah, I assume maybe because it's higher, more boosted, maybe closer, the two fluxes may be closer together, but I'm not sure.
That's excellent question. Yeah, I can definitely see that happening. Although I'm not, even if it gets a little bit better, I'm not sure it's gonna be like a huge difference. So this, I took the, the Dune flux prediction. There's like a website. I took the optimized horn design thing. It's supposed to be the most updated flux.
Okay.
But I will be interested in checking that. That's a great question.
Okay, thank you.
Thanks. Okay, so first, just because geometry, the near detector doesn't work perfectly. But there's another reason that's a problem, in that for oscillation calculation, we always, use the true neutrino energy on the x-axis. But you can never measure that in your detector because we don't measure the neutrino. We measure everything it produces. So instead of so whatever we measure, it's always as a function of reconstructed energy, not true energy. And the same applies in the far detector too. So you have to map, there has to be a map between what you measure of the neutrino energy to the truth, which is not perfect. So for these two reasons and some other details, near detector it definitely helps with the cross-section uncertainty, but it doesn't cancel it entirely. Okay, so then the key of how cross-section impact energy oscillation measurement is through energy reconstruction. So now let's look at that in a bit more detail. So let's say this is a theorist illustration of how Dune works. It's a liquid argon time projection chamber, which to me just means it's a big box of liquid argon. And neutrino coming in, which you do not see, and it hits argon nucleus. And then say this is nu mu. So because it's charge current interaction, you have there's an outgoing muon that you can clearly measure. And then because there's a lot of energy, so there's additional, protons, pions, and neutrons that may get knocked out. So most of these hadronic particles tend to have kinetic energy of, a few hundred MeV to maybe a couple GeV. And this detector basically sees all charged particles all charged particle tracks above some threshold. And the threshold is so low that let's just ignore it for now. Okay, so so in this particular example I draw, if it's true, then you can see the muon, proton, pion, but you miss the neutron. So this means that if this is true, then how will we reconstruct neutrino energy? Well, you just sum up the energy of all outgoing particles. And the only thing you're missing is neutron, meaning that the only thing we actually need to simulate from theory is neutron energy fraction. You can get everything else wrong, but as long as on the event by event basis, or on average, the neutron energy is predicted correctly, then average neutrino energy should be fine. That's sort of a key point. Does that make sense?
Yeah, it makes sense to me.
Okay, thanks. Okay, so which makes cross-section much easier. However, this is an actual simulation of what happens for a neutrino event in liquid argon. So here, the neutrino is injected at 0, 0. And then all charged particle depositions or tracks are shown in basically colored. So first we see this muon track as expected, very clear, good. And we also see for this event, there's protons and pions coming out, which is also good. But you see that even for protons and pions, they're not just a clean single track where you can measure its energy perfectly, but rather they will further reinteract. So both the proton and pion and the orange track, you see there's a vertex later downstream where it's turned into multiple tracks. So which means there's further, missing information, missing energy happening.
And hadronic interactions, proton and pi plus.
Yes.
Like inelastic scattering on nuclei, or?
Yes, this is just, say 1 GeV proton breaking up argon, producing 3 protons and 2 neutrons.
Right.
Yeah, and similarly for pion. And in addition, there's like a haze of purple dots throughout the whole plane. So those are basically charge energy deposition due to neutrons. Now I said neutrons are neutral, so you should not be able to see them. But in fact, neutron does something. So while it travels, it leaves nothing, but then occasionally it will hit argon, and it may excite argon, which then argon would decay through gammas. These de-excitation gammas are pretty small in energy, about MeV, but once you get a gamma, they'll turn into electron and leave a tiny, purple dot. So neutrons in some way do leave some energy. So basically, skipping a lot of details of what's happening in the final system, the key point is that if we see what energy is actually collected and what energy is missing, basically all aspects of the final state matters, in that whether you produce proton or pion affects how much quenching happens in liquid argon. If you don't know what it is, don't worry about it. It's some detector effects, but you have to know which one it is to correct for it. And as I said earlier, that even though threshold is very low, but because of this repeated reinteraction, more particles tend to get softer, so more particles does fall below threshold. So then threshold effect does matter. And also, like Maxine asked, because there's further reinteraction, and every time proton break up argon, there's energy lost to nuclear breakup energy, which actually does add up to. So essentially, all of these things contribute to missing energy. So what it means is that to accurately map what you measure in the hadronic system to a neutrino energy, it matters that you're predicting how much energy goes to pion or proton. It matters what their spectrum are. It also matters how many final state particles there are, whether you produce 3 or 5 indicates different amount of nuclear energy, nuclear binding energy loss. So it turns out that it's not just produce neutrons that matters, but it's basically everything. And okay, so if we want to quantitatively evaluate which aspect matters the most, then of course we need, based on this list, you can tell that we do need detailed, accurate experimental input if we want to do a full, phenomenological study. And unfortunately, that's not quite available right now, because right now the one difficulty is there's many unknowns or confusion on the theory side, but almost equally so on the experimental side. So for example, here we carried out a simple exercise. So let's assume that cross-section is perfectly known. Let's just take one theory model and take it to be absolute truth with no uncertainty. Then let's see, how does energy reconstruction work, and what's the energy resolution of events, and just from the literature. And here's what we discovered. Aside from cross-section uncertainty, only because of the uncertainty on the experimental side, it turns out that things are very uncertain. So depends on different experimental input that we take, we get energy resolution that differ as, by basically a factor of 4. And all of these input we took seemed, reasonable at that time and were from, detailed experimental studies. So one difficulty that in terms of evaluating things quantitatively is it's very, very hard to pin down an accurate experimental input for like threshold, exactly what threshold you should take, very hard to find. So this makes systematic evaluation of the cross-section impact difficult, but that is very much ongoing process. So, but conceptually, I hope what I explained well is that we do not need cross-section prediction that's cross-section as a function of neutrino energy, like you might have thought in the beginning. But rather what we need is a full differential cross-section with respect to how many number of particles coming out and all of their spectrum and all of the particle species. I hope that makes sense. Okay. And in addition, so I illustrate the cross-section impact from measuring delta CP. As you can imagine, it also actually impacts a lot of BSM searches that people are proposing in long baseline experiments. So here I just show 2 examples. The first one is to look for dark matter, basically dark matter annihilation in the sun. And if the dark matter primarily decay to annihilate to say pions, which then would cascade down, and that would come out in the form of basically hundreds of MeV neutrinos. One could look for these neutrinos, basically, they should be coming directly from the sun. And here is a paper that proposed a search, and the signature they're looking for, of course, to rely on the angular cut, meaning that you know these neutrinos will be coming from the sun, so you would expect the particles from these neutrino interaction to be pointing away from the sun, and that's the angular distribution of this these two solid lines, and that's on top of an isotropic background. So, but of course, this assumes that you actually know from a cross-section perspective what are the angular distribution of the outgoing particles, and which actually has very large uncertainty, so which would impact sensitivity for such searches. And in a similar spirit, so the right panel shows a different work, which proposed to look for a light scalar that's charged under B minus L. So the signature for this is for neutrino interaction, this neutrino can basically Bremsstrahlung a phi, which then would skew the kinematics of this neutrino interaction. So you can look for it. So then the signal for this model are in the two colored region, where because you are radiating an extra phi, so you would expect large missing PT from these exotic signal events. Whereas for standard model background neutrino interaction, there's not large missing PT. So that's the gray area. And then this obviously the sensitivity comes from the separation of these two regions. But obviously this rely on the fact that you do know roughly know the missing PT distribution of standard model interactions, and they're small. And it's not clear that's the case. So I just want to highlight that there's, in addition to just standard model neutrino interaction, a lot of BSM searches also rely on knowing some particular aspect of neutrino interaction kinematics well, and they are subject to basically uncertainties on cross-section. Okay, so hopefully that concludes my part of how do cross-section uncertainty impact oscillation measurement, and let me know if there's any questions at this point. Okay. Now, then let's move on to the next part. What are the current theoretical uncertainties? Okay, so let's say the thing that we want to calculate is neutrino interacting with argon with a neutrino energy of about 0.5 GeV to 5 GeV. And how this is practically calculated, and which is called impulse approximation, which works fairly well, is to break up this step into two. So first, you compute how neutrino interact with proton or neutron. And then you basically put this interaction vertex into a argon environment. And argon is made up 18 protons and 22 neutrons, but it doesn't really matter for the purpose of this talk. And obviously for other neutrino experiments, instead of argon, it's something different like carbon or oxygen, but don't worry about that. Okay, so let's say this separation works pretty well. So then looking at this, you might think, okay, I can see that the second part is probably difficult because we have to know something about argon, and it's a big nucleus, so it might be difficult to understand its structure, etc. Which is correct. That part is definitely challenging. But the first part is probably simple because, well, we know how to simulate neutrino, how to understand neutrino interacting with proton or neutron. Well, it turns out that that's not the case. And I think one could argue that this is probably the more challenging and more critical part. So let's look at how it happens. So again, for this beam energy, let's just look at neutrino, say proton cross-section. At the high end of this beam, say 5 GeV, this is basically, deep inelastic scattering, which is something we ought to be familiar with. Neutrino, you're interacting with a quark degrees of freedom out of this proton, and we know how to compute this reasonably well. And we would expect the final state to hadronize and produce a few pions. So that works fine. But as the energy goes a bit lower, so let's say a couple GeV, instead of interacting with the quark degrees of freedom, the neutrino start to see the nucleon. So then in this case, you're interacting with a neutron, and then the baryonic resonance states start to form in the final state. So in this case, you can imagine neutrino interact with a neutron and turn into a delta resonance. And there's like 30 or so such resonance states that can pop up, which then this resonance quickly decay into nucleon plus meson. So the nucleon plus meson is what you actually see in the final state. And then if we go below 1 GeV, they start to enter a regime that's basically quasi-elastic scattering. So what it is it's only nucleons involved right now. So neutrino is just swapping neutrons and protons. Okay, so even though the energy of the beam is pretty narrow, it's a few GeV, it unfortunately covers a very tricky kinematic region where the hadronic side of degrees of freedom is nucleons, resonance, baryonic resonance states, and quarks. So there's not a single theoretical framework that can describe the entire phase space. And I just really want to emphasize this is neutrino-proton interaction. So this has nothing to do with the nuclear structure. It's just even for nucleon interaction, it's just very challenging. Okay, and let's look at this in a little more detail. So this is the phase space of DOOM. In 2 axes, so the x-axis, they say q square, so that's the 4 momentum transfer square of minus, and the y-axis is the Birkin X. Okay, so, and the heat map basically shows the event distribution of DOOM neutrino events. So, and their color. So let's go from the list from top to bottom. So the first is, okay, so there's DIS, and that should happen at the highest energy. So these are simulated in neutrino event generators. And what the event generator labels as DIS is basically the darkest purple band that has DIS next to it. Now you should be very alarmed if you actually read the axis labels, because this DIS has a Q square about 1 GeV. Q square of 1 GeV square, that is way too low in Q square for factorization to actually work. So despite this is called DIS and simulated as DIS, it's already very problematic because DIS should not work in this low energy. This is, for example, if you run Pythia straight out of, box, it doesn't even allow you to run at this low energy because it's not expected to work. But that's what we basically have, so we pretty much have to use it. And then if you see there's like this diagonal sort of stripes, there's actually quite a few of them. There's 2 probably most prominent one. So those are basically resonance state, because if it goes to a fixed baryonic resonance, it should be exactly one stripe. And the difficulty here is essentially you have to treat every single baryonic state as its own degrees of freedom. And there's just so many, there's like 30 of them. And there's no way to compute these things from first principle. So we have to rely on essentially scattering data to constrain these coefficients. And there are just too many resonance state and not enough data. So that's resonance state. And then on the very top, you see this blob, and that's quasi-elastic, where again, it's basically, neutrinos are turning neutrons into protons. Okay, so, and unfortunately for DOOM, the energy is such that you can see roughly the 3 channels have, roughly equal contributions. So they all matter, which obviously make things worse because they rely on very different theoretical treatment. Okay, so I just really want to drive the point home because I think sometimes now think about neutrino cross-section, people think, oh, this is a very difficult nuclear structure problem. Well, the nuclear structure part is definitely difficult. I would say the more difficult problem is simply the kinematics. We don't know how to do physics at 1 GeV square. That's just such a tricky region. And so what people do right now is we just manually brute force, like break up the phase space into distinct pieces. Of course, this causes problem because each pieces work in the phase space that don't necessarily apply. And in addition, there's really no controlled way of transition between different kinematic regions. And we'll see this later on very clearly. Okay, and another difficulty that this brings about is that this makes calculation difficult, sure. But in addition, because it is just not a controlled EFT setting, there's really no way to estimate theoretical uncertainty because there's no control parameter. So not only we have trouble of knowing that the calculation are not very good, it's also extremely hard to say exactly how bad is it. Okay. Okay, and another thing that another aspect of this calculation that makes it difficult, which I already alluded to in the beginning, is that from experimental side, we've seen that we need prediction of not just the total cross section, but the full exclusive cross section. And I guess I hope it's easy to think that it's obviously much harder to predict a fully exclusive cross section than an inclusive one. And the previous difficulty that I explained, and that's the difficulty we have on the inclusive cross section. So going from that to full exclusive prediction, it's just even much harder and much less controlled. Okay, so how do we actually do currently? So like I said, there's simply no way to estimate it from a theoretical control way, so we have to do something phenomenologically. And one thing I think obvious to try is to take two theoretical predictions and see how much they differ. And so in terms of, so that's what we did here. So let's just take two of the most popular event generators and look at how they differ in total cross-section. So I take Gibbel and Gini. Gini is pretty much the event generator used by all neutrino experimentalists. And Gibbel is a more theoretically motivated generator. So here I plot just the total event rate as a function of true neutrino energy here. So what I'm simply comparing is basically the total cross-section across the 1 to 6 GeV. And you can see here that even at the total cross-section level, these two generators differ already by like 20%. Again, this should be compared to the 5% scale that I said in the beginning. So this probably should be alarming that, at the very inclusive level, things already differ so much. But of course, this is not so satisfying because, both theory could be more wrong, in some other direction. So the real error could be much larger. Or maybe one generator actually does almost perfectly and the other one just very bad. So then that's not really fair representation of the actual theoretical error. So then what we can do is, of course, take theory prediction to some sort of data. And there are a few choices available. The first one is, of course, because the ultimate thing we want to predict is neutrino nucleus interaction, we can compare to that data. And here the tricky part is, although we do have in recent years, neutrino oscillation experiments have collected a lot of data. These data tend to suffer from pretty poor pretty poor statistics, pretty large systematic errors. I mean, it's just very hard to carry out very precise measurement in neutrino experiment. And so then we can take one step back, say, how about we take electron nucleus scattering data? So just to be clear, so I'm talking about electron interacting with nucleus with a photon exchange. So the process is different from neutrino scattering. One is W exchange, one is photon. But they should shine some light on the current situation because, as I said, the difficult part of this problem is not that we can't compute a neutrino vertex to many loops, but it's how to deal with the hadronic system. And certainly there's similarity between how to deal with the hadronic system for a photon exchange versus a W exchange. So that should be helpful. But unfortunately, there's still not much data on electron nucleus scattering. So then let's take one more step back. What about electron proton scattering data? Because this should be the simplest thing that one can compute if eventually we want to build up to neutrino nucleus scattering. And finally, we're in luck. So it turns out there's a lot of electron proton scattering in the relevant phase space for long baseline experiment. And these are very high quality data. So let's look at how they do. So next, I'm going to show a few panels of such comparison. And just to set up what the measurement actually shows is the following. So a fixed energy neutrino beam with basically no error bars. So 2.4 GeV electron coming in, interacting with a single proton. And then you put the detector at a fixed scattering angle. So in the first panel, it's 20 degrees. So this outgoing electron is measured at 20 degrees, where you're measuring the energy of the outgoing electron. And obviously there's also other hadronic stuff coming out, and those are not measured. So you're only measuring things at 20 degrees of this electron. So this is this is called inclusive cross-section. And the cross-section is plotted as a function of energy transfer. That's just 2.4 GeV minus the outgoing energy of the electron. And the data are black points in both panels, and they're the same. And we can already see that, this is a very high quality data. The error bars are very small in both y-axis and the x-axis. So energy resolution is superb for electrons, and statistics is superb. So data quality is very high, no further comment needed. And so then we compare this to 2 neutrino generator prediction. So just to be extra clear, so neutrino generators can also have run in electron nucleus mode, and that's what we run. So this is really apples to apples prediction. And again, we just use Gini and Gibu, for the rest of the talk. And so let's look at the left panel first. So the Gini total that should be compared to the black data points are the solid purple line. And it's just very far off. And the correspondingly in the right panel, the total line you should compare to data is this solid green line. Okay, so look at the total. I guess first it should be alarming that Gini is basically off by like a factor of 2. And again, this is electron proton, so this is quite horrible. But that's not so telling on the physics front. So what's actually happening here? So as I said, in generators, phase space are broken, but basically brute force. So then the total cross-section actually has 2 main contributions. One is resonance production. So that's the red dashed line in both panels. We can see that also the right panel looks a bit cleaner. So let's focus on that. So let's say that it actually looks pretty good in that, the first peak is the delta resonance, and that's the leading one. That's just its own. And then you see a second and third peak. So actually there's like 4 or 5 resonances contributing to second and third peak. So it's difficult to isolate them. But basically all the peak structure and, and most of the things underneath that are from resonance production. And we can see that Gini resonance it gets the position right, but the amplitude are like quite off. And in addition, there's this DIS channel here. So if we trust the thing on the right, then basically there's not much DIS. There should not be much DIS in this phase space. But according to Gini, there's quite a bit of DIS contribution, and it has an interesting shape. And so this basically reflects what I said before, that the actual DIS in where it's valid should have pretty small error bar, not this level. But because what neutrino generator calls DIS is actually very different from what we think of DIS, this component is pretty random in the phase space. That's why the generators completely disagree. Okay, and basically there's a pretty good coverage of electron-proton scattering at a variety of different energy and different angles. So we can look at a couple more of them. But they basically tell a consistent story. For example, this one, it's a slightly higher beam energy, 3.2 GeV, and a slightly different beam angle. And we see the data, basically similarly to what you expect, there's still 3 sort of peaky structure from resonance production, but this time because of the angle, it's a bit more tilted. And similarly, Gini just consistently to be like a factor of 2 off almost. But we now also start to see Gibu having trouble. Now, there's one particular region I want to point out. This is, look at the sharp rise between 1.4 to 1.6 in Gibu. So the blue dashed line basically rise up vertically. So this is basically artifacts of that, as I said, because DIS is not applied correctly, and we don't know where it should truncate or should cut off. So in generators, this is so far this done essentially artificially. They decide on some random variable and say above this we use some formula, below this we use a different one, and clearly it's not physical because we can see this artificial feature. But this is a real problem in that there's actually no known physics solution. So we see stuff like this, and additionally there's another interesting feature one can point out is, again, look at Gibu at the very high end, so between 1.6 to 2.0, you see this overlap between resonance and DIS, and this is again a real physical problem in that at this kinematic region there's no clear distinction what is resonance production, what is DIS. So there's essentially double counting because some, yeah, just because there's no clear physical definition. So which channel belongs to which, it's like not entirely not clear cut. So the double counting problem is also a known problem that with no solution. So generator do whatever they can, and you can clearly see the problem here. And similarly, this problem that Genie has too. So between 1.6 and to 1.8, you can see that there's clearly double counting between residence and DIS, but it's just a bit worse. Okay, there's other angles and energies that we can look at, but overall, they all tell a consistent story. So first is, if we just want a number out of it, then at the inclusive level, roughly Genies tend to be off by somewhere between 50 to 80%. And Gibu definitely does significantly better, but still on average, it gets about 20 to 30% wrong. And again, I want to remind you that, remember, eventually we're probably aiming at something that to be accurate as 5% at inclusive cross-section. So at the very basic electron proton inclusive cross-section level, even 20 to 30% are like just not good enough. And we see basically problems that we would expect just from theoretical consideration, that there's no clear separation of what is residence, what is DIS. There's no place that, there's no way to know exactly what you call DIS start to kick in. So we see all these artifacts in event generators, but there's no solution yet. And in addition, I also want to point out that something that's not physics, but that's frustrating, is that through such comparison, you just have to take my word for it. One can review a lot of implementation errors. And they're not physics, but they do, they affect the prediction, so it makes everything more, just more complicated.
So Shirley, in the previous plots, you have predictions from neutrino generators, but are there predictions from other generators that are not, promising to reproduce neutrino data, but would reproduce the electron proton scattering? And how, I imagine, how well do they do? They probably do a lot better, but how much better?
Great question. So do you mean that are there event generators that are not neutrino event generators, but from different community that just simply focus on? Oh, that's an excellent question. So let's see. So the most obvious one that comes to my mind are event generators like Fluka or Giant, because they cover basically all phase space of physics. And that we do know. In fact, I'll show a plot later that indeed Giant does way worse than neutrino event generator in this phase space. Which I'll explain that. That's after we saw the result. We realized that in hindsight that should be expected. So those type of simulation packages don't do better. And I would say probably not, because, for example, you may know, actually, Gibu did not start out being a neutrino event generator, right? Gibu started out being a heavy ion event generator, which they actually had electron for a long time, and neutrino is a pretty recent thing for them. They added neutrino maybe 5-8 years ago. So in that sense, you can see Gibu does do better than Genie, but it's still not great. So
is it a fair statement to say that this data is basically unexplained, as far as, I mean, we know how to reproduce certain features or parts of the data, but you're saying that a comprehensive description doesn't exist, even in the electron sector?
Yeah, that's what I'm saying, yes. And if you think about it, it should not be surprising in a sense, we're talking about like energy transfer or Q square at about 1 GeV. That's where, that's where perturbation QCD versus QCD happens.
Right.
So, and the thing that matters is the hadronic site, how proton gets excited into different baryonic state. And eventually, when does that excitation hard enough that, it start to essentially break up into quarks? That's a very much of a non-predictive QCD problem. So the fact that I would say the generators don't do well, that should be expected.
And the Q squareds here are fixed, or in these plots that you have?
Oh, a great question. So not quite. So basically Q square vary with energy transfer. So across the whole x-axis, as energy transfer change, Q square also changes. But roughly 1 GeV square is just a a very rough number I'm quoting.
Okay.
Right.
Are there any data one could use for axial vector currents?
Great question. Yeah, so that's the sad part. So yes, there is like there's this bubble chamber data from long time ago from Argonne and Brookhaven.
But with neutrinos specifically, right?
Exactly. So right. So Argonne and Brookhaven took neutrino proton interaction bubble chamber data from way back in the days, and those two data sets are what people use to build the axial part of this interaction. But as you can imagine, that's like quite old data, and there's a whole ongoing investigation of the data set don't seem to be consistent with each other, like exactly. And the data set itself, of course, is it's not super precise.
Well, what I meant is that is there any way of gaining any further information by, say, taking pions and trying to shoot them at protons and so on? Because the pions and protons, well, not at least at the naive level, have axial interactions.
Yes, great question. Yes, so in fact, pion data is used. Is used to, I think, to constrain part of the axial interaction, and that's that's very much used. But I think it's a similar situation in that there's a very limited data set. Yes, but you're absolutely right that that data set is useful. And
I think even, in fact, some of the cross-sections that are fed into these generators are related to those cross-sections via, various PCAC and CVC and so on. And even, to do that in these very simplified models, then they have to use this data of pion proton scattering to constrain that piece. But they are, not expected to hold very well these assumptions of PCAC and CVC in this low Q squared. So that's the only point that I know these cross sections enter here.
I mean, I would say that, how well do you expect PCAC to work? Maybe, I don't know, 10% or something. And I would say that's actually not bad because given eventually it may not be good enough, but like given the current status, I would say that part uncertainty would not be considered like a deal breaker yet, because I mean, like we're talking about a factor of 2 here, right?
Yeah. Well.
So if eventually, hopefully 10 years from now, we will be talking about, a 5% thing or 2% thing, but we're very far from that yet.
All right.
Okay. So, right. So then, okay, just a very brief remark on the nucleoside in that, okay, so you might think, okay, so because electron proton does so horribly, electron argon must be just orders of magnitude off. And in fact, at the inclusive level, that is actually the opposite case. So here, what I'm showing is only data, no simulation. But their data sets basically taking at the same electron nucleus scattering energy and angle, and where they are swapping out the nuclear target and go. So the left is, from hydrogen to, actually, I'm not sure what that is, like 197 AU. And on the right, it's some energy and angle going from helium to iron. So here, what I'm saying, what I want to show is just the data shows that at the inclusive level, pretty much the effect of putting a proton into a nucleus is just you smear out features. So the left, we can see that on the hydrogen, there's there's 3 resonance structure peaks that got smeared out once we enter a nucleus. But aside from that, things basically scale. Oh, sorry. Everything is on the same line because I am dividing out the nuclear mass number. So, say carbon and iron are on top of each other is just to say that basically carbon is, some cross-section times 12, and iron is some cross-section times 15, times 56. And that works reasonably well at inclusive level. Similarly, on the right, you see that there's a first peak that basically got smeared out as you go from light to heavier nuclei. But for the majority of the phase space, everything basically scaled linearly as a function of nuclear mass. Now, this is not to say that nuclear effect does not matter, because how nuclear effect plays in a role is on the exclusive final state. This is just to say that because so far I'm only looking at inclusive data, the inclusive data is not a ideal testing ideal system to test nuclear effects, because they just tend to they tend to do pretty simple things that most generators can reproduce. And also, this also shows that because things do get smeared out, if you actually draw the similar comparison in the heavier nuclei, the difference actually tend to look a bit better, just because things are more smeared out, so they look more, agree with each other. Okay, so that concludes the section of what are the current theoretical uncertainties, and I will say it's not very good. And I really want to emphasize the point that the difficulty is not about nuclear structure. That's part of the problem, but I would say that's not the most problem. The problem is it's really, we don't know how to compute hadronic physics at 1 GeV². So even proton interaction is very difficult to reproduce. Okay, so the last part, I'll try to go quickly. How to improve? So I think the first thing to say is certainly more, given that we already cannot reproduce existing current data, certainly more theoretical is needed. For example, how to do better at dealing with the double counting between resident state and DIS, and how to more accurately test how much factorization breakdown at this kind of a phase space. But one thing is certain is that certainly more data is further needed. I think conceptually the reason for this is hopefully we can find better theoretical description. But because this is not in the control parameters phase space, we know that whatever theory that we can come up with, it's not going to be some sort of EFT. It will be some mix mash of phenometrical models, better controlled, hopefully, but not fully systematically controlled. So we even with better theory, we still need aggressive data testing to make sure that the model is adequate. And the current data's coverage is very poor. So the proton coverage is good, but we also want coverage on electron nucleus. And there's only one single set on electron-argon scattering. The best covered nucleus is carbon. So here, this figure shows the carbon data coverage. Again, the gray map is just the phase space at the event density map of DOOM, and the red points are data coverage. And you see that I switched X and Y axis, so the figure looks different. But the key point is the data, part of the data plane is well covered, but not where the most DOOM event stay. So the darkest blob is actually not covered really. So that's a problem, but we want to really cover the whole space. And the biggest problem I would say is that there's only inclusive data. There's very few exclusive data, even on electron. And that's actually the final part that enters neutrino experiments, so that matters a lot. Okay, and it turns out that the proposed LDMAX experiment is an ideal setup to take more cross-section data. So here's the basic setup. You have a few GeV electron beam and a Hadra target, and it may recoil against a nucleus. And with the outgoing electron, it may emit to a dark matter pair, or it may emit a mediator which then decay to our dark matter pair. And the experiment is designed to look for dark matter where you are looking for, you can measure every single particle of the coming out of the system. And because you know the incoming energy and momentum of the electron perfectly, you can look for missing momentum and energy. And that's the strategy to look for dark matter. And the panel shows the phase 1 sensitivity as a function of coupling and dark matter mass. And excitingly, earlier this year, the planning stage of LDMAX is funded. Now, for a cross-section, for someone who's been working on cross-section, I look at the setup and I thought, oh, what a perfect setup for cross-section measurement. So it turns out that just the default dark matter setup is basically ideal for cross-section measurement, because first, we have a 4 GeV electron beam, and you can measure everything in the forward 40 degrees. So what this means in the phase space is that you can measure everything that's to the left and bottom of the 40-degree line. And you see that it really covers like the majority of the dune phase space. And then because it's like the target is just a thin, solid, it's very easy to take it out and swap and put in different nuclei. And in addition, most importantly, the design already include measuring all outgoing final state hadronic particle, even including neutrons. So this is really a perfect setup for cross-section measurement. And here it just shows that I think, for someone who work on neutrino experiments, the specs for this kind of experiment is just so high, in that this is to test that, efficiency, detector resolution, and threshold are not going to be a problem. So the left, I show the number of electrons predicted for this experiment using different event generators. And Matthias, and this, I think this sort of answers your question. For example, we did wonder, how does Geon do? We included Geon prediction. And we also tried different versions of Genie just to be on the safe side. And this is pass-through detector simulation. So detector resolution is already included, but there's no natural effect. And we see that the Geon is very off from event generators. And there is actually some data we can check in this region. It turned out that neutrino event generator does better. So Geon is way off. But even among neutrino generator, there's easily a factor of 2 discrepancy, which we shouldn't be surprised at this point because we already kind of saw that from before. And the right panel just to show a hadronic measurement where we plot the number of pions as a function of pion energy. And here I just want to highlight, so you see there's a little kink in the blue line that's basically tilt up at the lowest energy. And this is one generator predict this. It comes from the fact that pion energy gets softened as they propagate out of a nucleus. So this is a nuclear effect. And we can see that the threshold is low enough that if this indeed happened at this level, then LDMX should easily be able to distinguish it. So detector specs are superb, basically, perfectly adequate to discriminate against different event generators. Okay. So that brings me to my conclusion. I hope I've convinced you that GeV neutrino nucleus scattering is very important to long baseline neutrino experiments, not only to their bread butter delta CP and mass hierarchy measurement, but also to many BSM tests that people are proposing. And right now there's no complete theoretical framework because of the awkward kinematics. And that makes the calculation difficult, but also very difficult to give an accurate uncertainty estimate. And more theory is definitely needed, and more data is definitely needed. I would say the data side seems to be going in the right direction. There's the LDMAX, and there's also a couple other proposals. So more data, there is a way to take more data. But on the theory side, it's a lot more tricky. It's not clear how to go forward. So if you have any ideas, they're extremely welcome. Okay, so that's it. Thanks.
All right, thank you, Shirley. Virtual applauses. If anyone has any questions, they can just unmute themselves. Otherwise, I have one quite obvious, which is, apart from LDMX, aren't there dedicated, I mean, you would think that there would be dedicated experiments for electron-proton scattering that are happening? So places like JLab, for instance.
Yes, great question. So yes, so and the other proposal that I was basically implying is this class 12 experiment, and that is at JLab. But it's interesting that you mentioned that because this is dedicated electron scattering measurement. But JLab is primarily a nuclear facility. So they actually had a bit of, so when they were proposing to do this measurement for neutrino physics, they, I think the perception is, well, okay, so neutrino physics, that is not JLab's priority. But in any case, they still get a beam time, so hopefully that data will happen. But it's not like, there's any lab that is, this is our top priority, we will definitely do this, we'll do this as fast as possible. That does not actually, I don't think that happens anywhere.
Okay. Any other questions for Shirley? Okay, if not, then we can thank her again virtually. And thank you so much for giving this online talk. Unfortunately, we can't have you here in Minnesota, but maybe sometime in the future.
Thanks very much.
Yeah.
Thank you.
Right. Thank you, Shirley.
Bye.
I'll stop.